Magnetic force between two current-carrying wires. Here's a common situation that you might see. You have two wires, each with current flowing through them, each of length L, and they're next to each other. Each wire is going to create a magnetic field around it. Remember the right-hand grip rule? When you have current flowing through a wire, there exists a magnetic field around it, shown here. Each wire will create a magnetic field that will exert a force on the other wire. Let's look at the force on wire 2 due to wire 1. So wire 1 is creating this magnetic field, and as you see, it's going to exert a force on that wire. Since the wires are separated by a distance d, the magnitude of the magnetic field generated by wire 1 at the location here is given by this equation. The strength of the field at this distance away from this wire is mu naught I1, because it's the current in this wire that's generating the field, over 2 pi d. The magnetic field due to wire 1 is everywhere here that it hits wire 2, it's perpendicular, and actually it's pointing straight down at that location. So the force on wire 2 due to wire 1 is we're going to use that ILB equation. Remember the force exerted on a current carrying wire? Now in ILB, the current is the current going through the wire that's feeling the force. So the amount of current flowing through I2 is going to be what is included in this equation. The force on wire 2 has to do with the current in wire 2, the length of wire 2, which happens to be the same as the length of wire 1, and it's due to the magnetic field created by wire 1, which is why we have B sub 1. That's what's exerting the force. If we substitute the value of B1 that we found on the previous slide, so instead of B1 we put all of this in there, we can rearrange and we get this equation, which is not on the AP2 equation sheet. This is something that you would have to derive by combining those previous two equations. We can carry out a similar analysis for the force that wire 2 exerts on wire 1, or we could just use Newton's third law, because it also works on magnetic and electrical forces, to state that the magnitudes of those two forces must be equal and their directions are opposite. So the force that 2 exerts on 1 is equal to the force that 1 exerts on 2, and it is given by this expression that we derived by combining two other equations. Now, let's find the direction of each force. Are these wires going to be attracted to each other or repelled by each other? All right, so this can get a little tricky. First, we use the right-hand grip rule for wire 1, and we see that there is a magnetic field going around it. Once again, it's hard to draw 3D, but because the current is that way, you point your thumb in the direction and your fingers wrap around, and so therefore the field will be into the page to the right of the wire and out of the page to the left of the wire. Now, wire 2 is to the right, therefore the field will be going into the page. Then we use the other right-hand rule to figure out the direction of the force. So you point your fingers in the direction of the current of I2. You rotate your palm to face the computer screen since the field is into the page, and your thumb points to the left. That is the direction of the force on wire 2. Now, we could just use Newton's third law, which states that if the force on 2 is to the left, the force on 1 must be to the right. However, we can also do the same exact steps again to achieve the same result. If we use the right-hand grip rule for wire 2, we see that the magnetic field created by this wire is into the page to the right of the wire, like that, and then out of the page to the left of the wire, which is where I1 is. So it's out of the page. Use the other right-hand rule, point your fingers that way, you point your palm away from the computer screen, and your thumb points to the right. So In conclusion, when you have two wires that have their currents going in the same direction, they attract each other, which kind of goes against what we've learned before. We've previously learned that opposites attract, but in this particular situation that does arise often, currents in the same direction will attract each other. What about if the currents are going in opposite directions? You can do the same steps again, and you'll find that the force on wire 2 is to the right. You can do the same thing again for wire 1. We can use right-hand grip rule to determine what the field looks like around this wire, which is out of the page to the right of the wire, into the page to the left of the wire. Since this wire is to the left, that means it's feeling a magnetic force or a magnetic field that it is experiencing a magnetic field that is into the page here. Then use right-hand rule to determine that because its current is this way and the field is into the page, it's experiencing a force to the left. So when you have two wires next to each other where their currents are going in opposite directions, they repel each other. What is the magnitude and direction of the magnetic force between two parallel wires that are 30 centimeters long and 5 centimeters apart if each carries a current of 40 amps in the same direction? If you are wondering where this equation came from, go back to the previous slides and derive it again. This is the force between two parallel wires. So we can substitute in all of our givens. So we have the currents, which are the same. We have the length of the wire, which is the same for both, which is important. We have 2 pi d, the distance between them. See how we've converted all of those centimeters into meters, which standard units. And we get a force of 1.9 times 10 to the negative third newtons. Now we need to find the direction of the force. The wires will be attracted to each other. As we previously concluded, parallel wires carrying current in the same direction attract each other.